it's time to start with the opening talk that is going to be really astonishing because we have here Sir John Pendry, professor of at Imperial College of London, that is very well known worldwide because his very, very relevant achievements. As everybody knows, Professor Pendry is the father of several key issues that now is working in real field. And now key issues that is working in real field, he at this time have another theories that that is going to be very important for new technologies and for new real equipments in the future. So Professor Pendry have enormous accounts of top quality papers in which everyone can realize about the achievements of Professor Pendry. But if we try to summarize in the key, more important achievements, maybe we can soon realize that we can do a breakdown in three key topics. One is the achievement of metamaterials. Another one is the perfect lens. And probably another one is one what is key issue in this talk, that is the invisibility of the cloaks, in which, as Professor Pendry are going to explain, well, we can see, but not see the object by doing engineering with the light. So Professor Pendry is this kind of rare human beings that sometimes appear among us, that with very humble position, he is always ready to share his knowledge with everyone and many other things. And he is doing very, very important contributions for the humanity. Maybe someday Professor Pendry, that have many awards and honors, maybe one day we are going to see with the highest honor in this environment, that is the Nobel Prize. We hope that Professor Pendry someday will prize it with this very important honor, because the high quality and the wide contribution for the humans at this moment. So no more words. I think that everyone are expected to hear Professor Pendry. And now, Professor Pendry, we are very happy to have you in the room, and we are very happy to hear you. Thank you very much.
Well, thank you very much for that kind introduction, some of which was possibly overstated. It's a pleasure to be here in Santander. I visit northern Spain regularly, mainly to San Sebastian. I come there every year. But my first time in Santander, so thank you very much. Some years ago, we created some new materials which weren't known at that time, but have now become known as metamaterials. And these had very radical properties, and they were difficult to design and control by the old methods. So we also had to think of some new design theory, and that was called transformation optics. And then we had to think, well, how do we tell people about this? So you show people a bunch of copper wires, you show people some equations, and they go, So we had to think of a way of really, really surprising people. And at that time, the Harry Potter stories were very popular. And we thought, well, if we could make something invisible, maybe some people would be interested. Maybe we could get a few kids interested in science. And that's the way it turned out. So let me turn to the talk. And this is the old way, very old way, of thinking about how light moves. It was actually jointly invented by two guys. We normally call this Snell's law, which tells how light diffracts at a surface. But in fact, Descartes also had the same idea. Newton did as well, but he didn't acknowledge these two guys, even though it was later that that was the sort of guy Newton was. And you might ask, why does this law is still taught, even though it tells nothing about the many things we already know about light, such as the fact that light is a wave. This assumes that light is a particle. We also know that this isn't the full story of light at a surface. There's some reflection as well. Snell's law doesn't know about that. And yet, we still use it. And the reason we still use it is that it puts a picture in our mind of what light is doing and how we might change the materials and change the design if we want to do something different. And that's the power, the visual power of Snell's law. But unfortunately, it's not good enough for our purposes. So I want to spend a few moments at the beginning of the talk telling things that you probably know already, but perhaps a slightly different slant on them from the one you know. So what light really consists of is not a stream of particles. It consists of electric and magnetic fields. And the field lines are what we're going to use to replace the rays of light, because if you use electric and magnetic field lines, it's possible to have an exact, at the classical level, description of electromagnetism. Now, fields were introduced by this guy, Michael Faraday, and he had an interesting way of looking at a magnetic force. Now, at that time, people thought of magnetic, and indeed any force, as action at a distance. So, for example, the force between two magnetic poles is inversely proportional to the distance between them, just as is the force between two gravitation objects. And the force acts along the line connecting the two particles. But Faraday said, no, that's not a good way of looking at it. And what he said was that it's in fact an intermediary, that one of the poles, or both of them actually, create something called a field. And the field is there whether or not it's acting on another particle. The field creates the force, but the field is an entity in itself. And he said, if you don't believe me, I'll show you the field. So here is a magnet, and on top he's put some paper. And as kids, most of us did this experiment, put some iron filings, and the filings align with the field lines. And he said, there is the magnetic field. Now that concept is, first of all, it goes against a law called, in philosophy, called Occam's razor, which says that if you can explain something with two theories, the simplest one is the one you choose. So action at a distance is the simplest one. But sometimes when you choose something more complicated, it can lead on to other things. This man was a son of a blacksmith, born in poverty, knew no mathematics. He created the concept of a field, which is the basis of most of modern physics. Astonishing. So we're going to use the fields that that Faraday envisaged, and he also used them to enunciate another law of electromagnetic induction. And he noticed that, well, if you wrap a coil around the magnet and connect it to a meter, nothing happens unless you move the magnet. So he said that a changing magnetic field creates an electric field. It creates an electromagnetic force on the electrons, forces them around the copper circuit, and makes a reading here. Now, you could not have that law in terms of action at a distance, because it involves the rate at which field lines cut across a copper wire and propel a force in this direction. You try and formulate that in terms of action at a distance, you can't. So this complication, this breaking of Occam's law, was the key to understanding this first key component of electromagnetic field, that a magnetic field can turn into an electrical field. But before we know what light is, we had to have another law. And this was the law which James Clerk Maxwell produced. So actually, Maxwell and Faraday were great friends. Maxwell was much younger than Faraday, but they lived near to one another in London. Faraday worked at the Royal Institution, and Maxwell was a professor at King's College at that time. And this is the way in mathematics that Maxwell wrote down Faraday's law of induction, saying that a changing magnetic field produces an electric field. But he realized that this had to be complemented with another law, which was that if you have a changing electric field, that produces a magnetic field. And this was the key to understanding light, because he showed his equations to Kelvin, and Kelvin said, there should be a wave-like solution of this. So Maxwell, being a brilliant mathematician, soon found the waves, and he calculated the velocity. Actually, he didn't calculate the velocity because immediately, because there was one thing that was left to do. In those days, electricity and magnetism were measured in different units. Electricity was measured in something called stat volts, and magnetism was measured in terms of electrical currents. And the ratio between the two was his velocity of his waves. And to determine the ratio between the two, he did a very nice experiment, which students at the Cavendish Laboratory can repeat, not on the original apparatus, but something like it. And amazingly, this velocity turned out to be the velocity of light. That, I think, was one of the most astonishing revelations of the 19th century, that suddenly there was this unification of things we knew about, but we didn't really know they were connected: electricity, magnetism, and light. And the argument for the extra term in Maxwell's equations, so here you have an electrical current, but Maxwell said that a change of the electrical field should be equivalent to a current, because if you do this integral here of the magnetic field, that if you then put a surface over that, cut it through the current, then that should be equal to another surface cutting through the electrical lines of force there. Whilst we're introducing the greats of history, here's somebody who doesn't need any introduction. Einstein was a great admirer of Maxwell. He had a portrait of Maxwell above his fireplace in Princeton, where he spent his last years. And when he did his general theory of relativity, the general theory, as I'm sure you know, involves the concept that space isn't empty. And this was a very important concept because there's a huge paradox with light, because light is a wave. It's a wave in something. Water waves, sound waves are waves in air, water waves are water moving. What's moving when you have light? And people went to all sorts of contortions to ask, well, you know, what is it that's moving? And they invented this name for what it's moving in. It was called the luminiferous ether. Isn't that a wonderful word, luminiferous ether? But Einstein said, that's all okay, don't worry, but the vacuum isn't empty. It is something, just as a piece of wood or a piece of metal is an object, a material with properties. Einstein thought of space as a material with properties, and the property that space has is geometry. So if you squash the space with a gravitational field, then you change something called the metric, which is how big we measure something in that space. And his metric, called it G, is just the measure of how much space is squashed or stretched by a gravitational field. And one thing that was noted was that if you write Maxwell's equations in the very general terms that Einstein proposed, accounting for the fact that space may be bent or squashed, then you find that the metric G comes in the same place as does the refractive index. So it's not really surprising that when you try to observe a star, where starlight is passing by the sun, you can only do that when there's an eclipse, that there's some bending of the starlight near the sun, because the sun bends space. That's like bending the refractive index. So you have a gigantic but very weak lens surrounding the sun, which displaces the position of stars. And it was that observation by Eddington in 1919 that put Einstein's theory on a very serious basis. So we take those concepts, we're going to work with the field lines, and what we want to do is to find a material that will move these field lines as we wish. So I start with a field line that just happens to be going in a straight line, and I draw some Cartesian coordinates here to just record what I'm doing to space. And then I imagine that the space is made of rubber, and I'm going to stretch and pull it. And as I stretch it, the field line behaves as though it's glued to the rubber, and it moves with the space. And so you can arrange the field lines more or less as you please. And then when you're done, you can use Einstein's formula to calculate the metric of a bent space through the transformation from here to here. That's why it's called transformation optics. And so you can find the refractive index, or more specifically, the values of epsilon mu you need to send that field line along that trajectory. And that is what we're going to use to design the cloak. So if you like mathematics more, then this is the formula for epsilon and mu to send the field line in this direction in terms of the transformation here. This is the first derivative of the coordinate transformation, and that gives you the transformation. And we use that for another purpose in 1996, but it was well known before that, and that's the key to transformation optics. There is, in fact, a simpler way of looking at it. So if you squash space like this, the simplest squashing of space, then you can ask, what are the values, new values of epsilon mu in the squashed space? And the answer is that along the direction of squashing, the values of epsilon and mu are reduced by the same amount, alpha, which is the squashing factor. Perpendicular to the direction of squashing, epsilon mu are increased by 1 upon alpha. So decrease, increase. And then you could actually crawl over this distortion with a ruler and a protractor, and you could ask, what is the squashing in the 3 separate directions? And without any recourse to algebra, just using geometry, you can find out what values of epsilon mu are there. So that's our argument for using the field lines as an intuitive replacement of Snell's law. Of course, these transformation optics laws are more complicated, but they do have an intuitive basis, and they provide a picture of what's going on in these systems. Well, so what we want to do to implement these transformations is to have a material with very, very general properties. And that's where these metamaterials come in, because they have the property that they can be designed to fulfill many, many requirements which are not possible with natural materials. So here's the idea. An ordinary material consists of molecules, and when you polarize that medium, it's the polarization of the individual molecules that gives rise to the average polarization, averaged over many billions of molecules inside the material. But those entities you polarize, they don't have to be atoms or molecules. They can be a little bigger, and the only requirement is that you can average over them, so there must be many inside 1 cubic wavelength of the radiation. And so they can be little elements like nanostructures that you design. And so a metamaterial is a material whose properties derive from the geometry of its internal components rather than the chemistry. Of course, you need chemistry as well because you've got to make these things, but the key is the geometry. And here's an early example of that. This idea of making things with interesting responses through their structure came about through some consultancy work at Marconi. And Mike Wiltshire actually made one of these structures. So these are little copper rings. If you put a magnetic field along the axis here, a current flows in the ring. That creates a magnetic response. So this is magnetism without magnets. This is designed to work at 10 gigahertz, wavelength of 10 centimeters. The diameter is about 5 millimeters here. So lots and lots of rings inside a square wavelength here. And actually, if you notice, these rings have a little cut in them here, so the current can't flow freely around the ring. It has to charge a capacitor here, and that capacitor plus the inductance of the ring makes a resonant circuit. And that gives rise to some very interesting properties, because with a resonator, the response is quite interesting. So if you take a kid's swing and you just let it go, it has a natural resonant frequency. If you push it slowly, it will go in the direction that you push. But if you try to shake it too fast, faster than the resonance frequency, it will do this. Yeah? Don't try it when your kid's on the swing. And so the response of a resonant circuit actually reverses when you tune through the resonance. So you can have a positive response one side and a negative response the other. So this particular arrangement provided a very interesting property which people have been seeking for years, and that was that it had a magnetic permeability which was negative above the resonant frequency. And that had been sought because many years ago, in 1968, Victor Veselago said, it would be very interesting if we could have something with a refractive index that was negative. Then all kinds of crazy things go on to happen. And if I have time, I probably won't have, I might tell you a little bit about negative refraction. But the requirements to produce it were twofold. One was that you had to have a negative response to electricity, and the second, a negative response to magnetic fields. And it was the second one that was really difficult, in fact impossible. There are no materials in nature which show both those things at the same time. However, David Smith, who's been my longtime collaborator on all this invisibility stuff, saw our ideas that actually it was a conference Eli Bonovitz organized in Laguna Beach. And I met David there for the first time, and I talked about these materials. And David put together our negative magnetism rings and these rods, which you can barely see, which are actually on the other side of the circuit board. The dimensions, again, are about 5 millimeters. And these two together, the rods and the rings, produced negative refraction. And this was the first negative refracting structure made at UCSD. There were other structures, but I'm going to have to pass over those. So this is negative refraction. Positive refraction is like this when the ray emerges into the material on the opposite side to the normal. And if you have negative refraction, this happens. And that gives all sorts of crazy things. Here are some metamaterials which were designed to show negative refraction at optical frequencies or near optical frequencies. Here's the fishnet structure, which comprises alternate layers of dielectric and metal, silver and magnesium fluoride. And the dimension here is a micron. This is an electron micrograph of that structure made by Zhang Zhang's group in Berkeley, California. So there's been many, many applications of metamaterials. It's a growing field. There are thousands and thousands of papers written on it each year. And it's just been a lot of fun. But when is he going to talk about invisibility? I hear you cry. The first thing to say about invisibility is that it's not enough to paint something black. That's conventional stealth, and all it does is stop the object reflecting light. But as you see from this drawing here, it's not enough to be black, because you'll still have a shadow. And the really difficult problem of invisibility is to get rid of the shadow. This guy, by the way, some of you may recognize, he's Peter Pan. And if you know the story of Peter Pan, he's the little boy who lost his shadow. So when the shadow's gone, Peter is invisible. So how do we do that? So remember those field lines? I can move them around. I'm going to draw a circle here, and inside that circle, sphere, whatever, I'm going to expel all the field lines. So no light can ever get in there. You can't see what's inside. So it's hidden, but it's not yet invisible. But I'm going to draw another circle around here. I should have drawn it in the figure, I'm sorry. And I'm going to say that when I do this distortion of space that I mentioned, I can't allow myself to make any distortion outside this bigger circle. And the region between the little one and the big one, that's the cloaking region. And so the way I do this is to make a hole here, and I shove all of space out of this middle region here, and I push space into this region here, taking all of the light with me, okay? So if you like, that's the transformation which does it. It takes this bit of space, and this transformation will compress all of this space into this blue region here, leaving this entirely empty. You can do what you want in there. Nobody cares. Can't see you, can't get at you. You can't get out if you're in there. And from this transformation, you can find what the refractive index is, or epsilon mu more precisely, that will actually make that cloak. And when you've done that, the light will flow like water around the hidden region. And the key thing is that if you confine your distortion of space to the cloak, and you don't distort space outside the cloak, then if you don't distort space, you don't move the light around. So the light just continues as it was before, out here, But then inside, it does this chicane, like a skier avoiding a tree, goes smoothly round and back where it is. Now, think of the challenge of writing. I give you Maxwell's equations. I give you a powerful computer. I give you COMSOL or something. And I say, design a distribution of epsilon mu that does this. How would you do it? OK, let's make a start. So we come into the material, and we want to make a left turn because we want to head around this. OK, we steer around, OK. And then, oh, what do I do here? Somehow the light has to remember what happened here. So, OK, let's send it somewhere. And then what about this other ray of light, which comes on at a different angle and comes out somewhere else? That's also got to go undisturbed. It's a huge design problem. It's a non-local problem. What happens here affects what happens there. And that's one of the trickiest problems of physics. But at a blow, without a computer, you can write down analytically what the solution is. And that's the power of transformation optics. That's the story we wanted to tell through invisibility. That's the real message, not amusing kids. Though that's also important, where, of course, when you amuse them, you can also enthuse them about science. But that's the real message. So this business of smoothly distorting where light goes is not unknown. For example, if you have a mirage, when you have hot air, which is less dense, less refracting, below cool air, typically a hot surface, then the light will be continuously refracted like this. So you'll see something that isn't really there, which you interpret as water because you see a reflection of the sky, and what you know is water that does that. You sometimes see this, a very poor picture from the web, I'm sorry, but sometimes in the summer, in the distance when the tarmac gets very hot, you can see what appears to be a wet road, and then when you get there, it's perfectly dry, and it's this mirage effect here. So that's the sort of thing we want to do, continuously bend light. And the first device which did this was this electromagnetic cloak here, comprising these split rings of the metamaterials. And this whole thing was put in a two-dimensional waveguide. It was produced by David Smith's team way back in 2006. So that was for radar waves. But then people said, well, what about optical cloaks? Because that's what we're really interested in. And that produced something tricky, because even if you have this concept of a metamaterial, you've still got to make the metamaterial out of something. And really, at optical frequencies, materials are getting very tired. The electrons don't move so fast because relative to the frequency of light. And the materials issue is a really tricky one. Lots of things are lossy. So we had to simplify the design of a cloak in order that people could make one at optical frequencies. And so this was the way our thoughts progressed. So one way of looking at a cloak is to think of it as a kind of lens. So a regular lens makes things appear bigger than they really are. But you can also make lenses that make things smaller than they really are. And you can make a special sort of lens that makes things infinitely small. Then they're invisible. Can't see anything that's infinitely small. There are actually three ways you might do this. So you might take an object and use a lens to effectively squash it down to a point. Point light objects are invisible. Or you could squash it down to a wire, a one-dimensional object. Very thin wires are invisible. Or you could squash it down to a very thin plate. Unfortunately, a thin plate isn't invisible, because it turns out if you do that, epsilon is very, very large here. It's a very good mirror. So we had to think, well, OK, the point of going through these three steps is that each one is easier to fabricate. at optical frequencies. And so this two-dimensional idea of squashing something down into a mirror, you know, you can see a mirror, but where could you hide it? What about putting it on another mirror? So an infinitely thin mirror on top of a mirror makes a mirror. How do you know there are two mirrors there? You don't. That's the first one's infinitely thin. So that's the idea. Squash things down so that they're infinitely thin, and then put them on a mirror, or a ground plane, as we say in radar parlance. So here's the idea for doing that. You start with a ground plane, an empty space, and then you create a refractive index profile by compressing in the vertical direction all these cells here. And that leaves a little hidden region here. But if you do the compressing right, the thing viewed from the top will seem just like it was before. You won't notice this compression if there's no compression outside this region here, as with the cloak I've already spoken about. And here's the refractive index profile from that. This is work done by Jensen Lee, who is now back in Hong Kong, having worked with me some years. Here's a simulation of what happens if you shine light on a bent mirror. So you put a laser beam over this thing, and then the facets of the cloak, the uncloak of the mirror, of the lamp, create two beams of light instead of the one from the mirror, so it goes flash, flash. And then if you put the cloak in place, you get just one beam of light again, and you've effectively flattened this tunnel here so that it thinks it's part of the background mirror. And actually, it's one of the very few instances where you don't need a metamaterial. So the guys in Birmingham and some guys in Singapore actually made this cloak. So if you do this compression in exactly the right way, you make an anisotropic material, and if you have the parameters right, that material is calcite. And they got two pretty big crystals of calcite, which is birefringent from China. And the Birmingham guys created this hidden space here. And this works at optical frequencies. And so here's just a ray trajectory showing that it does its stuff. Now, to demonstrate the cloak, they did the following. They took the alphabet, and they looked at the alphabet first without the cloak in place. So here you've got a mirror with a kink in it, which is covering the cavity where you're going to hide something. And because there's a kink in the mirror, you only see the first bit of the alphabet, A, B, C, D, and then the middle bit's missing, R, S, T, U. And by the way, this is in glorious Technicolor because there's been some argument about whether the cloak's broadband, and this is real white light. And so here's the cloak in place, and the center of the alphabet is restored. So it does look like a flat mirror because now you can see H, I, J, K, L, and it works. And there's only a slightest bit of chromatic aberration. So cloaks are finite band, but not narrow band. Okay. So I could tell you more about cloaking for static magnetic fields, but I want to go on to tell you about negative refractive index, because I think you'll find that fun. So Veselago said that it's possible to do this if you have epsilon mu negative. And now we have epsilon mu negative. But you might ask, well, why? Why is it interesting? Negative numbers, we can do imaginary numbers. What's the big deal about making the refractive index negative? Well, it turns out that if you do that, all sorts of very, very strange things happen in optics. Here's one of the least strange things. So Veselago pointed out that you can make a lens out of this. So if you have diverging rays of light here, negative refraction brings the light back to a focus at the axis here. So if you filled your fish pond with negative refracting water, your fish will be swimming in thin air above the water. That's just another crazy thing. And Veselago knew that his negative material would act as a lens. But more recently, not all that recently, in 2000, I realized something else. That this lens didn't only focus rays, it also was able, if you made it perfectly, to produce a perfect image. And that violates something called Abbe's law, which says that you can only see something with light that is bigger than something like half the wavelength of light. And that was thought to be a rule of physics. It isn't. It's a rule that is specific to the sort of lenses that we've been using for thousands of years. But if you use a different lens, the Veselago lens, the law doesn't apply. So let me try and explain why Veselago's lens violates this law that's been believed for a long time. So here's the picture that Victor Veselago gave to us of focusing, but I want to say that that picture is far more general. But first I'm going to create a negative refractive index medium using the principles of transformation optics, okay? So I'm going to squash some space. And as I squash it, remember that law. It said, for example, that if you squash something, the refractive index perpendicular to the permeability and permittivity perpendicular to that direction increases. And the more you squash the space, the bigger those guys get. And eventually, if I squash them really hard and make the space very compressed, epsilon mu, their values go up towards infinity. And then, if I'm of a mathematical turn of mind, I push past the singularity. You know what happens to 1 upon x. It goes up to infinity, and then down to minus infinity. So those values of epsilon mu go up to infinity, down to minus infinity, and then you push a bit more until they are the values you want, minus 1, minus 1. And then you've created the lens. But in the meantime, you've done something really peculiar to space. What's happened? This space is different from ordinary space. It actually has what we call 3 manifolds or surfaces on which things exist at the same time. So you think the light is doing this, going through the light. What the light thinks it's doing is doing this, this, and this as it goes around this maze here. And so if you have a focus here, that focus will be passed once and twice again. And since transformation optics is exact at the level of Maxwell's equations, if this focus is something as small as an atom emitting light, the focus here will be equally perfect, provided that you have the perfect materials. There's the rub, of course. So that created a bit of a fuss at the time. A lot of people said it was rubbish, huge arguments, but eventually all the dust settled, and I think that's accepted now. And it's led to a whole field of sub-wavelength optics, and I'll be talking about that in more detail tomorrow morning. Well, there are other things you can do with negative refraction. So in a way, this lens is unusual, but it's very boring because you want a lens to not just to see something, you want it to make it bigger or smaller or whatever. And this lens is so perfect, it makes the image exactly the same size as the object. But again, you can, of course, the transformation optics, and you can bend that lens around, stretch it and pull it a bit, and then you can make a spherical lens. And here are the values as epsilon mu. for the various regions. And what this lens does is that everything inside this red sphere here, viewed from outside, will appear as if it's in this red circle here, which is bigger than the lens itself. So this is free space, okay. So that's a bit strange. Why is it strange? I use the analogy of a milk bottle, but nobody has milk bottles these days. But if you imagine this was a glass container, have you ever looked at objects in a glass? Have you noticed that if there's a clear fluid like water or gin inside them, that the fluid goes right to the edge of the glass? Yeah? Have a look, it does. Very simple to explain. And that's because any ray of light that strikes the glass will actually enter the liquid. And so you always see liquid right at the edge, unless it's really, really thick glass. But this glass is different, because any ray that strikes the red circle, which is outside the glass, will see the milk, right? So the milk would appear to be out here. That's a kind of weird bottle with the milk spilling out of it. It doesn't actually spill, of course, but it appears to be outside of it. So that's a very, very strange thing. And yeah, I'm getting near the end of my time. Oops. Yeah. So another thing you can do with this thing is to say, how do I create a shadow with a really small object? If an object is smaller than the wavelength of light, it doesn't make a shadow, because light diffracts around it, and the fact that the smaller the wavelength allows the light to close up behind. So you can't make an object with a shadow with a really small object, except if you put it in a lens. So Wei-Sheng Wei, my postdoc, my student at the time, said, well, what if we put something really, really black inside this lens, put the lens around it, and then this black stuff appears to be really big. This all stuff here is smaller than the wavelength. This is the wavelength here. It's of the order of the wavelength, but it appears like a really big black object. And here's some light coming in from the left. You can see the waves here, and it creates this really big shadow from something small. So there are other really weird things you can do. But what I want to do now, in the few minutes remaining to me, is we've tried to be entertaining for the past half hour or so, telling you about Harry Potter stuff. But what I want to do is, in the last few minutes, to get a little serious and say this is partly about having fun. That's why I do science. But the reason I'm paid for doing science is that some people happen to think that some of the things we do are useful. So here's a good example. This is an outfit called Intellectual Ventures. They hold many of the patents on metamaterials. And they aren't just a bunch of lawyers. They actually have some laboratories, and they spin out companies. And one of the companies they spun out is called Chimeta. And it makes satellite communications receivers. Now, the regular ones, the cheap ones, come as a dish, which has to be steerable to follow the satellite. That's expensive. Well, it's not so expensive. It's a couple of $1,000 maybe. No, it's more. It's 10,000. It is heavy. It takes a lot of electricity to drive the electric motor. The other sort is what's called a phased array, which is a slab of silicon, and that does the pointing business to the satellite electronically. That's really expensive. That's about $100,000. Now, using tunable metamaterials, you can actually make a phased array, which is pretty cheap. And Chimeta are marketing these. Here's one of their satellite receivers, and it's aimed at journalists. It's aimed at energy mining, aid agencies in Africa where there's no cell phone network, disaster recovery where the phone network's down, and remote temporary office. But also, Chimeta have a contract with Toyota, who are planning to put one of these receivers in the roof of every car that they build, so they can talk to your car in real time. Whether you'd like that or not, I'm not sure, but that's what they plan to do. And this car they drove across America to the motor show a couple of years ago, just to prove the concept. What else? You can use this phase array, cheap phase array technology to, instead of having terahertz scanning, you know, this business at the airport like that takes 3 seconds and a complete pain. What if you could have something that, excuse me? Sorry, I've lost my drift here. What if you had something that could just scan a beam across you as you walked to the check-in? That would be really good for you and help airport security as well. That's one of the things they plan to do. Here's another application. Capasso invented the quantum cascade laser for producing terahertz beams. Problem with terahertz is that quantum of energy is very small, so an electron is normally possessed of 1 or 2 eV in a semiconductor. If a lot of that will be wasted if you tried to get a terahertz radiation in one transition. So Capasso let the electron fall down a waterfall, a little step at a time, and that emitted terahertz radiation. The only problem is that there's a mismatch between the scale of the semiconductor structure and the wavelength of the radiation that you're creating. So to create better coupling, they plan a metamaterial which surrounds the semiconductor laser, grabs that energy, and radiates it more efficiently because of the higher density of states. What's the next one? Oh, yes, this is just a simple lens, which is designed for Boeing. This is an idea from a colleague of mine, Richard Sims. He's founding a company. And the idea here is that in MRI, magnetic resonance imaging, or nuclear magnetic resonance, as it's properly called. For some reason, they changed the name. If you want a good image, you have to put the pickup coil, which detects these magnetic signals from the nuclear spins, really close to where they're coming from. And if you're doing a high-resolution image of the heart, that means taking a wire with a coil on the end of it, cutting a vein in your leg, shoving the coil up the vein to the heart, and then you can get a really good picture of the heart. But there's a bit of an issue there because it's a copper wire, and the RF frequencies in MRI resonate in the body at about 1 meter. And so that wire may get hot. If you're careful, it doesn't, but that is a hazard. And if it gets hot and sticks to the side of the vein, not good. So the argument went as follows. Why take a beautiful magnetic signal in an environment which is magnetically almost completely silent? The body has virtually no magnetic noise in it, and turn it into an electrical signal where it has to compete with this huge cacophony of electrical noise which the body produces. Okay. Why not keep it as a magnetic signal? And so what Richard did was to design a wire for magnetism. It consists of these metamaterial loops, and then he can take this MRI-safe cable down your vein and give a safe and quiet image of the heart. So that concludes what I have to say, a serious conclusion to a light-hearted talk. I did give a similar talk with a few of the modern details missing some time ago. Here's a New Scientist article. I believe these slides are available to you, so these references are available. And also there's a very nice report from a school which is very similar to this one, founded by Professor Harry Messel in Sydney, and this one was in 2011, and I write up some of the things there. You might like to look at those on the web. So thank you for your attention, and I'm very happy to answer any questions that you may have.
Thank you very much, Professor Pendry, for your very nice and interesting talk. And from a very long period of time, I realized that if we exclude the external noise, in this room, 100 people, no noise at all. So this means that the aspect signal noise ratio was really incredible. I never better say it because the next talk is going to be in communication. And as everybody in the room knows, the signal to noise ratio is the quality factor, the key quality factor. So all this suggests that everyone in the room was the open mouth here in your talk, your interesting talk, that
there is another explanation. They might have been asleep.
Okay. So this means that everyone was very interested in this matter because it seemed like science fiction. But it was like science fiction several years ago, but not today, because your work. So now the talk is open for questions. So every questions, of course, asking in the right political way. Yeah, freedom is key issue. We are in the university, so freedom is a key issue. But of course, with the due political norms. Okay. So every question is welcome. Please, questions. Yeah, first one.
Very bad. Thank you.
First of all, thank you a lot for your presentation. Quite nice, quite interesting. Maybe there was an acoustic cloak here in this room for the reasons of the aspect ratio. And I want to ask you about the perfect lenses. When you published your paper about perfect lenses, there was one comment about the losses because this is a metallic metamaterial and anything else. Okay. What about now with the development of this epsilon and mu, negative epsilon and mu, with silicon, with semiconductor materials? It's maybe an answer for this.
Okay. May I give the audience a little bit of background here? You're obviously a bit of an expert here. So what I didn't tell is how this perfect lens does its trick. And what it has to do is to grab what we call the near field, which are electrical signals which decay very strongly away from the surface, and so you just can't receive them a long way off. And what the lens does is to use a resonance again to amplify these things. So people think to amplify things, you have to have some power, but you don't. And the example is a wine glass, and you've heard the story that if you have a singer, it has to be a female singer with a higher voice. She sings at the wine glass, and after a few seconds, it breaks if it's a really good wine glass. And what she's doing is singing at the resonant frequency of the glass. The glass harvests the energy over a few seconds, and then, if it's fragile, it will burst. And this is what the lens does. It takes these very, very weak signals, and it feeds them into a resonance. Now, your point is that if there's some loss in the material, loss really kills resonances, because if you're trying to build up energy and something's eating away at the energy, and loss is, people ask me, what's the resolution of your imperfect lens? And the answer is, it's decided by the loss. So yes, what you say is we can now make materials with negative epsilon, but where the imaginary part of epsilon, which is a loss, is smaller than it was before. So yes, things are developing all the time. Watch this space. Thank you. Excellent question.
Thank you very much for this question. Another question in the other side of the room.
First of all, I'd also like to thank you for this beautiful lecture. And Maybe it's a silly question, but like you make a metamaterial cloak, can you also make like a metamaterial black hole, but by inversing what you want to achieve, like by compressing?
Yes, again, I'll talk about related things tomorrow. Instead of stretching space, you can also compress it. So you can make a really weird transformation, which is called an inversion. And it takes points at infinity and puts them at the origin. And so you start with the situation where waves are going out to infinity, take a long time to get there, and then in the new transform situation, which you can build physically, the waves are going towards a point, but they never get there. And in that respect, it's like a black hole. But the black hole is not quite a black hole because the black hole does something different, which is very important. It emits something called Hawking radiation. And that's because a real black hole has got gravitational energy. This has just got a refractive index. So it does the vanishing light trick of falling very slowly, but it's not quite there. It doesn't actually make the radiation.
Yeah, of course.
Had we been able to do that, Stephen would got his Nobel Prize before he died, because the missing thing from the Hawking radiation, which you need to get a Nobel Prize, is there has to be an experiment. And real Hawking radiation is so weak that nobody has seen it yet. And sadly, Stephen died this year, so never to be.
Thank you.
Any other question? Yeah, please.
So when you're talking about this invisibility cloak in the sense of lens, and regarding to the first question, you were mentioning this resolution of the lens. Yeah. So in what terms is the resolution characterized? Is it like, for example, in other resolution limitation, the resolution is like the minimum distance between points that you can resolve.
Yeah.
So in terms of invisibility cloaks, is it the contrast?
In terms of the perfect lens, you
Yeah,
mean? Yes.
yeah.
In terms of the perfect lens, it's it's indeed the distance between 2 points that can be resolved. Another way of putting that is that you make the image out of Fourier components, and the higher the order of the Fourier component, the more detailed the object. So if you have a lot of Fourier components, you have very, very sharp resolution. But the higher the order of the Fourier component, the more firmly they're stuck to the object, and you have to amplify them more. So it's harder and harder to get the higher Fourier components, and that's where the loss comes in, because it stops you doing the really hard jobs of the very finest Fourier components.
And the loss is correlated to the oscillator model inside the lens, is it?
That's right, yes. What people have used is the plasmons in silver, which give you a negative epsilon. And that takes you pathway towards a perfect lens. But silver is a very highly conducting material, but it's still got a little bit of resistance. And so people have only got to about 5 times the wavelength limit to resolution so far, 5 or 6 times. But they have broken the Abbe law, but obviously we're never going to get infinitely perfect resolution because, I mean, 2 things. One is that you're never going to get perfect materials. And the second, even if you did, what happens is that the later Fourier components arrive later in time than the first ones. So you know these images that appear on the web, and first of all they appear a bit fuzzy, and then more Fourier components arrive. That's the way the perfect lens works. So you switch the perfect lens on, and it just has the ordinary resolution, and gradually the other Fourier components come in, and the picture gets better and better. But if you want it perfect, you'd have to wait infinitely long.
Thank you very much. Another question, please? Yes.
Thank you for your nice presentation. My question is regarding the dispersion in the negative index. If we have a waveguide with negative index material, what would happen to the dispersion? Especially in one of your slides, we have seen a mirror-on-mirror configuration, and in the final stage, we have seen some dispersion and aberration in the picture.
By dispersion, you mean dependence on frequency?
Yes, exactly.
Yes, okay. That's a shrewd question. Let me go back. So let me explain it this way. On the face of it, this negative refraction doesn't seem so strange, but there is, I wish I had another slide here that does it, but I'll have to do it with a pointer. I remind you that there's a conservation law at a surface, and that is that if you associate a wave vector with this ray here, the wave vector points in the same direction as the pointing vector, which is where the ray is going. So the wave vector parallel to the surface points in this direction, okay, also in this direction. Now, the wave vector inside the medium, parallel to the surface, has to be the same as the wave vector outside. So this is traveling in a different direction, but in order to get the same parallel wave vector, its length has to increase. So by the time you take its length times the sine of that angle, the wave vector is conserved. But that's impossible here, you might think, because the wave vector here is pointing in this direction, and if you assume that the wave vector is parallel to where the ray is going, it can never, however long this is, point in the right direction. And that was the source of a huge argument about whether negative refraction was possible, which was resolved by the following observation. The wave vector doesn't have to be, it has to be in an isotropic material parallel to the ray, but it doesn't have to be in the same direction. It can point in the opposite direction. And that's exactly what happens. The wave vector points in that direction, and so you can actually get this matching at the surface. Now, if the wave vector and the ray point in opposite directions, that means the group and the phase velocity are different, and they're actually opposed. And the only way that can happen is that if you have dispersion, because the group velocity, which is the ray velocity, is d omega by dk, and the phase velocity is omega over k. And if those are different, then it has to be dispersive. So you can't have anything that's negative without dispersion. And the so-called perfect lens disperses like crazy. And if it didn't, you'd break all sorts of physical laws, this being the first one of them. So thank you for your question.
Okay, one last question. Okay, thank you very much.
Thank you.